Welcome again to EET 260 microcontroller applications. This is week one. We've had two lectures about the course syllabus and the course map, and now we're going to actually start talking about microcontrollers. So let's get started with that. So you're probably familiar with this book. When you built your Bobot, you used this book, What's a Microcontroller, and came with your kit, and you've probably read quite a bit of things from this. If not, then it's right here for you. But it's very similar to the Bobot manual, and you'll recognize a lot of the things in it. The PDF for this book will be available in the Blackboard Learn site. It is available, as we discussed in that course documents section, reference documents. So let's talk a little bit about microcontrollers. And I like to start out, when I was a boy, you've probably heard that the very first real digital computers used relays and vacuum tubes. And so you can read this as well as I can. With the advent of the transistor and the integrated circuit, size and power consumption have been drastically reduced. But into the 60s, even so-called mini computers took a few equipment racks, and the mainframe computer still required a special room, special power delivery considerations. In the late 60s and early 70s saw the introduction of useful computers in tabletop and partial rack sizes. These mini computers for use not just in general computing, but also in factory automation. And you'd see them in laboratories, CNC machines. They began to show up in defense. They'd show up in test equipment for testing things maybe in the manufacturing process and that sort of thing. So computing was getting smaller and of course more powerful as it was going along. I mean, the largest computers, as we said, still took up a lot of room and power, but it was the situation was improving. And so from an architecture standpoint, nearly every computer consists of a central processing unit, or CPU, and you can see that in this diagram. And it's sort of the main sequencing unit. It's sort of the brain, and it accesses some kind of memory where program and data are stored. There's a memory for program called program memory, and memory for data called data memory. And sometimes they could be the same block of memory. Other times they're completely separate blocks of memory. But the point is, this CPU was like a chef who read his recipe instructions out of this memory. And the computer could then interact with the outside world through, input devices and return results via output devices. CPU, memory, input and output. Like I says here, the classic, if not simplistic, model of a computer. And the architecture of computers, how these things were connected, grew in sophistication and speed, and and continues to. Microprocessors spend a lot of energy, the designers do, in trying to get this architecture right. Like how many ways can the CPU be made faster, and how, can it do multiple things at once, or can it do parts of many things in sequence, and how can we make memory faster, and what can we do for input output. And so and talking to disk drives where you store data for a long term, that's part of this input output system over here. So that's kind of the way big computers took off, and miniaturization happened, and things were on a good trend. In the mid-70s, experience gained in digital logic integrated circuits and handheld calculator ICs, probably other things too, led to the introduction of small CPUs on a single integrated circuit. And this was considered a really big breakthrough. These one-chip integrated central processing units became known as microcomputers or microprocessors. Microprocessors is probably the right word for the single chip. And maybe microcomputer is a good name for a board that uses a microprocessor, something like that, or a box that contains a board that uses a microprocessor. The market for and the application of these chips just exploded into every area where electronics could provide a benefit, adding the new feature of programmability. So every time you had something that used to work previously, things maybe had dials, so you could make some settings, but you could only set certain things, and it was very hard to make something generally programmable. And these microprocessors brought that kind of flexibility. They brought, the flexibility you have with a computer and being able to write programs. They brought it to regular everyday electronics, so that things could be much smarter, much more sophisticated, and think about cars with the amount of computing that's going on in cars nowadays. Just to get the air and gas mixture just right, or to run, electric cars, all the things that happen nowadays. A lot of times the efficiency is provided by a programmable algorithm that runs in some kind of a programmable device, like a computer kind of device. Still, a product involving a microprocessor, in those days, in the mid-70s, required memory chips and some I/O circuitry with a few chips, and there were still spatial and spatial and economical barriers to entry for programmability into many new devices, especially those involving consumer electronics, where the prices are really, squeezed, and there's drastic downward pressure on the prices. Sometime not long after the microprocessor explosion, a few companies began to integrate a CPU, so like a microprocessor, some memory, and some I/O on the same integrated circuit. The result was the microcontroller, and it started an explosion in electronics applications and marketing quite similar to that resulting from the microprocessor. So where the microprocessor just exploded, and the first personal computers and lots of programmable and powerful devices began to appear, the microcontroller made that extend down to devices that were within the grasp of consumers. And you think of some of the things back in the 70s and 80s and 90s, like VCRs and DVD players, and along with all sorts of other things, these things could really benefit from a smart controlling device. And so that's what microcontrollers did, is they could replace lots of digital logic and lots of other circuitry, because they had this general purpose programmable nature that all that value previously embedded in hardwired electronics could now be accomplished in a programmable fashion. And maybe the same chip could be used in several different products. The only thing that would be different is the program. I say the only thing. The program is a pretty significant thing, but it allowed you to bring this level of features into products that people hadn't seen before. Um, Today, both genres dominate computing. You see micro processors, such as the Intel and AMD, and other manufacturers' processors that drive really high-end PCs and servers and laptops and that sort of thing. And you see the microcontrollers, driving the handheld smartphone market and so on and so forth. And you see other microcontrollers that handle things like TV remotes and thermostats and microwave ovens and that sort of thing. The last thing I was saying down here, the fastest and most capable computers are those based on microprocessors and graphics processing units, or graphical processing units, or GPUs, as evidenced by the ICs used in personal computers. Nowadays, the game market has driven the graphics processing to involve essentially computing elements that are so fast and so powerful, and there are so many of them on one chip that people have grabbed hold of these processing units, not just for video and for all the complicated live display of computer games and artificial realities and in-game environments, but also they become, when you batch a bunch of them together, they become extremely powerful simulators. So all this stuff about searching for proteins and molecules and viruses and studying that kind of stuff, or studying the bending of beams, or the any kind of problem, these graphics processor units have become at least as important as microprocessors, maybe even more so. And the fastest supercomputers built today are built with these graphics processing units, or GPUs. So what's a microcontroller? Microcontrollers have become completely pervasive in electronic products, from kitchen appliances, medical devices, radios, TVs, printers, 3D printers, tools. Yeah, I mean, even some of the batteries that you charge up now use some intelligence in the battery to keep track of how much charge the battery has left in it, and how much charge it can take before it's full, or how much charge it can give before it's empty. And so all these things now, you could because a computer program can capture a lot of complexity. These microcontrollers are able to be used in a wide variety of products, and they can eliminate a lot of other parts and add all this flexibility. Arguably, the area that has changed our lives more than most others is that of mobile devices. Handheld calculators became personal digital assistants. If you've ever heard of a Palm Pilot in the late 80s, early 90s, which became cell phones, which became smartphones, which now include apps that work with a global positioning system, digital camera technology, biomedical sensing, like the Fitbit and that sort of thing. You can aim your smartphone at a portion of the night sky and see a display of which astronomical objects are in your field of view. That is, if you have all the tilt sensors and everything in your smartphone. You can take 20 or more pictures of an object around its circumference. This is pretty cool. And almost instantaneously acquire a solid body model of the object in digital form. You can then go take that and replicate it in a 3D printer. So great. Once more, what's a microcontroller? Here I'll take a shot at the definition. A microcontroller is a complete computing solution in one miniature package, be it on one integrated circuit, a system on a chip, or on a small printed circuit board, system on a board. Microprocessors are employed in general purpose computing, as experienced in personal computers and more powerful server systems. Microcontrollers are targeted at more specialized applications, whether for consumer or industrial electronics, where they are said to embed within where they're said to be embedded. Sorry, there's a word missing there. To be embedded within a given product. So such implementations are therefore called embedded systems. So a little bit of vocabulary there. So microcontrollers wind up on a board with a few other parts, and they're inside some box in a system that has very specific purpose. And so unlike a general purpose computer like a laptop, desktop, or server computer, embedded systems are kind of purpose built, as some people would say, and therefore the computing power is embedded inside the system, and we don't interact with it like we would a computer where we have a mouse and keyboard and display. That isn't to say we don't, that isn't to say we couldn't have a graphical display and a keyboard. They can, but we wouldn't in general load general apps and that kind of thing. The smartphone is really kind of pushed the boundary, because the parts used inside could be called microcontrollers, but at the same but by the same token, they have so much memory and have a screen and your ability to move around it with a touch interface. And they can bring up a graphical keyboard, and they can download apps and run actual programs. So, is a smartphone an embedded system, or is it a general purpose computing platform? So I guess the best answer there is yes. It's both, and that's what's happening with this. Often happens with technologies where there's kind of a bifurcation, that is a splitting of the technology, the microprocessor aiming toward the more powerful type thing and the microcontroller toward the lower end thing. And then as technology grows, the microcontroller now is overlapping with the lower end of the microprocessor world. And, to my estimation, who cares? We don't need to have too much vocabulary other than to kind of understand what people are saying when they use these words. So we talked about, when we looked at the course map, we talked about the basic stamp on a board of education, which is this board here. Hopefully you can see that. And the basic stamp is this unit here. It's kind of a system on a board, if you will. It has an actual microcontroller, and it has this 20 megahertz. It's kind of like a crystal. It's a ceramic resonator, but it's very much like a crystal. It works with a couple of pins on the microcontroller to set up the timing so that the microcontroller runs at a constant rate. And it has a little bit of extra program memory outside the chip. It has a voltage regulator because microprocessors generally want to run in a somewhat narrow voltage range. Digital logic to run efficiently needs to be able to count on its supply voltage being constant, and that's what a voltage regulator does. You can bring a higher voltage onto this board. The voltage regulator will then drop that voltage down to 5 volts so that this microprocessor runs properly, and so that all the input and output signals work between 0 and 5 volts. And there's some serial input-output here for talking to a computer. And actually, these 2 pins up here are part of this power circuit, these 2 pins on the upper right. This by itself is a microcontroller. They just wanted to add a few features and make the use of this thing a little bit easier. So they put it on a board, and you can call this whole board a microcontroller too, So that's the basic stamp. And, I went backwards. The Board of Education, or BOE, is what's in this picture. And it has a place to plug in your basic stamp right there. This picture shows a board without a basic stamp in it. But you plug in your basic stamp right there. You have an interface where you can connect a USB cable to your computer, and a virtual serial port is connected that way, and so you can talk to the microcontroller. And you have access to the microcontroller's pins. They bring out connectors here, so you can plug in wires and experiment with the thing. There are power supply pins arranged up here, and there's a general purpose prototyping board, or breadboard, if you like to call it that, in this white area. And just to remind you, you may have burned this into your memory by now, but just in case, the way these whiteboards work, each group of 5 holes is connected. So if you plug anything into any of these 5 holes, it's connected with metal underneath, conducting metal underneath. So that's the way you build circuits. And in Parallax, they actually show you pictorials. So if you're not sure, you can always follow the pictorials, but it's probably a good idea to be able to test yourself and make sure you can take a schematic and come up with a way to connect it on this board. You don't have to use the exact way the book does. But that's a board of education. Maybe that's a microcomputer. I don't know. That's more, the word microcomputer to me is a very very vague term. Sometimes general purpose computers were called microcomputers if they had a microprocessor. But this is a microcontroller board. How's that? Or it's an embedded system. But that's your board of education. Just a word about the cross-development of embedded systems here. As you built your Bobot, you used this process repeatedly and probably became second nature to you, but I just want to name it to kind of say something that's common with a lot of microcontroller development that goes on. Here is some laptop, and you can't really see it, but this is the PBasic editor. And we would say that is your integrated development environment. That is all the things you need in one program so that you can develop programs to talk to the basic stamp on this board right down here. This program includes the communication capabilities, so it can talk over this link here, this USB cable. We'll call that our dev system to target system link. Here's your development PC or dev PC right here, and this is your target embedded system, which in this case is a board of education, and it has a BS2 microcontroller in it. So just some vocabulary there. And this whole process is called cross-development because if you were writing applications for your computer, you would program the applications on the computer and then run them on the computer. In cross-development, you develop the programs on your computer, but then you have a communication link to the target system, so you can download the programs, and depending on the degree of sophistication of your microcontroller and your integrated development environment, you can run your program, interact with it, and have the program give you hints as to what's going on, so you can debug the program until you've got it working the way you want. Just a little more specificity here that you are probably aware of, but just want to kind of refresh your mind on it. Once again, we have the development system or dev PC. We have the target system, in this case, the Board of Education. And we have this dev PC to target system communication link, which is a USB cable. USB-A at the dev PC end, and USB mini B 5-pin at the Board of Education end. So a lot of things can happen here. You can download programs to your target system over this cable. The Arduino people, if you're familiar with Arduino processors, they like to call this process of going from your dev PC to the target system uploading. I've always called it downloading, but you're loading, that's for sure. You're moving something from your development PC to the target. You can receive messages in the debug terminal on the dev PC from your program running on the target. I'm pretty sure you've done this. You've used the pbasic debug command to send a message up here in something called the debug monitor or debug terminal. I'm sorry, and it can give you information about what's running in your program. Furthermore, you can also, in that same debug terminal, you can write a program so that the program running on the Board of Education requests information from the debug terminal on the dev PC, so that you can send numbers or codes or whatever you want from the PC down to your running program. So this red path here is downloading the program, and then it will start running. The blue path is hearing messages from the program in the debug terminal, and the green path is typing things in the debug terminal that are accepted by the running program on the target system. This is just a screenshot of the pbasic editor, and I'm just kind of making the point here that you in the pbasic editor, your program is in the main right-hand pane of the editor window, and if your program contains debug or debug in, then the debug terminal will appear. In this blue pane, the lower pane in the debug terminal, is where your system can send you messages and let you know what's going on. In this program, there's a statement that says debug, quote, your LED should now be blinking on/off, period, end of quote, and then sends a carriage return, a CR. And you can see on the debug terminal here, well, it's pretty fine print, but it says your LED should now be blinking on/off. So that message was sent from a running program on the target system. Not, we have the program listed here, but it's not running on this PC. The program has been downloaded and is running on the target system, and it sends this message back up to the blue pane in the debug terminal window. The white pane above it in the debug terminal is where you can type, if you've written your program to require input from you, the dev PC, the development PC, here's where you type that input, and that's when you use the debug in command in pbasic. So here's a program that does that. It simply it has a variable, which is a place in memory. A variable is nothing more than the name of a place that holds information in your microcontroller or computer or whatever system you have a variable on. And what it says here is do, and it has the loop, so this is going to run continually. It'll say enter a positive number from 1 to 255. It's a debug statement, so that'll appear on your dev PC in the blue pane of the debug terminal window. And there's a carriage return. And it says debug in dec username, user num. I'm sorry. And the user num is this variable we declared, and dec means you will type in a decimal number. The next statement that will execute will be a debug statement. It says that number squared is colon space, so that's in quotations. That's going to appear in the blue. and it'll type out, says dec usernum times usernum comma carriage return. So it's going to multiply the usernum by itself and print it out in decimal, and then print a carriage return. Hopefully that gives you an idea of the things that you can do. You can have the target system talk to you and have it show up in the blue pane of the debug terminal window, and you can have the system ask you for input that you will type in the white pane of the debug terminal window, and your running program using a debug in statement will grab that information and use it in processing. So let's talk a little bit about interfacing basics here, just digital input and output. This picture is from what's a microcontroller, and I should have attributed it, but you may have seen it in the book. A digital output, digital inputs and outputs occur via these conducting pins on the side of the microcontroller. That they're metal conducting pins, and each one has an identifier. This is called P14, and maybe it means pin 14 or something like that. And you can tell the microcontroller to switch, if this is being used as an output, if pin 14 is being used as an output, you can switch it to to 0 volts, which is called VSS on the microcontroller. The VSS equals ground equals 0 volts. So you can switch this output port to 0 volts. And what we have hooked up is we have a series 470 ohm resistor. Then we go through an LED. Notice how the flat side of the LED is connected to VSS or ground. And if both sides of this, if both of these sides here, both these wires are in essence connected to VSS, no current will flow because there's no voltage across this circuit, and you get no glow from your LED. The LED will not be on. If I then cause the P14 to be connected to VDD, which is approximately 5 volts, I will now have 5 volts across that same circuit. Some current will flow and the LED will turn on. And in this case, I don't know, maybe 6.5 milliamperes will turn on. That's enough to make the LED glow. So there's a really simple digital output. You can either make the pin be 0 volts out, or you can make it be 5 volts out. Here's an example of how they, in what's a microcontroller, they have a circuit where they've plugged in an LED and a resistor in the prototyping board, and that's what this figure describes. And to the left here, we have how it be represented in a schematic. We have P14 connected to a resistor that's in series with a light emitting diode, or LED, and the anode of the diode is connected to the resistor, and the cathode of the diode is connected to VSS or ground. So what happens here is if pin 14, again, if it's connected to 0 volts, no current will flow and the LED will not come on. Now in the pictorial diagram here, I made this note that kind of made an arrow pointing to the back side of this LED. The LEDs have this little flange that runs around, the LEDs have this little flange that runs around the bottom of the LED. And on the side of the LED that is the cathode, or the part that's intended to go toward VSS, that flange is flattened. And you can kind of roll it with your finger on a desk and tell when you've reached the flat side. Or if you look at it carefully, you can definitely see it. And that's how you know which side of the LED goes to VSS. And so one side of this LED is plugged into VSS. The other side, which is the anode, is plugged into one of the rows of 5 connected holes. One of the other holes in that same row is connected to a resistor, a 470 ohm yellow, violet, brown resistor. The other end of that resistor is plugged into the hole for P14, and that's P14 is the second hole from the top of that black 16 by 1 header that's right next to the white prototyping area or breadboard. So you can run a program like this one, and remember, you need to indicate what type of basic stamp you have in your program and the version of P-Basic you're using. You don't absolutely need the statement, but it's good practice. I put a statement in that says output 14. That means P14 will be explicitly configured as an output pin. I then had a debug statement, so the debug terminal will come up on your dev PC and it will say your LED should now be blinking on/off, period. Be a carriage return, and then it'll go into one of these do loops where it says do at the beginning and loop at the end, and it says high 14. Well, high 14 means make pin 14 drive out a high voltage level, or about 5 volts. Pause 1000 means pause for 1000 milliseconds, or 1 second. Then it says low 14, so 14 goes down to a 0 or 0 volts, and once again pause 1000 milliseconds or 1 second. So when you have the high 14 and you're put 5 volts on 14, the LED should glow for 1 second, then it will go off for 1 second, and then you just keep repeating that pattern. Digital inputs on microcontrollers, and specifically the basic stamp. Digital inputs and outputs in microcontrollers are usually gathered into groups or ports consisting of a number of individual input, output, or bidirectional lines. So input and output are the two different directions that a pin can go. In P-Basic, individual input or output lines are numbered from 1 to 15, but they're numbered in different ways in other microcontrollers. You just have to look at whatever microcontroller you're using. The value of any given line used as an input is captured, I left out the word by here, it's captured by the keyword in number sign, where number sign is replaced by a number from 0 to 15. So, for example, if the voltage on the pin called P3 is less than approximately 1.4 volts, in3 will return the value 0. If the voltage on the pin called P3 is greater than approximately 1.4 volts, in3 will return the value 1. So we don't really want to do too much playing around right in the area of 1.4 volts. We mostly want to see things like 5 volts and 0 volts, or we want to see, we want to definitely be much greater than 1.4 volts to indicate a 1, and much less than 1.4 volts to indicate a 0. And that's one of the things that's nice about digital electronics is if you can do that, then a little bit of noise on your wires won't matter too much, because as long as you're quite a bit below 1.4 volts or quite a bit above 1.4 volts, you'll be sure of whether you're seeing a 1 or a 0. And so you've seen how we drive out digital outputs. In essence, we sort of connect them to either VDD, which is 5 volts, or VSS, which is 0 volts. The inputs are brought in and they're compared. So the arrows show the inputs coming toward the microcontroller, and they're compared with a threshold voltage somewhere in the 1.4 volt area. And that's how we make the decision of whether that input is a high or a low. We can read a push button And this circuit's a little different than what you see in your book, but it's very commonly used in industry. We use something like a 10K resistor to connect the input to VDD so that the input looks like it's always a 1. But if you press the button, you will cause current to flow, and the input will be connected to VSS or ground or 0 volts. And so the program that's over here on the right contains one of these do loops, and the first line says debug in 3. And what that means is debug means it's going to print something to you, and the question mark means it's going to capture the value of input 3, the value of P3 in essence, and then it's going to wait a quarter of a second, 250 milliseconds, and do it again, and it's just going to do that continually. So if you run this program and you push the push button, before you push the push button, you should just continually see 1 being printed out on the console, on the debug terminal. But when you connect the button, it should pull the pin low, and you should see 0 printed out on the debug terminal. You can be a little more sophisticated if you like, and you can use the same input circuit on P3, and again, it will be, when the button is not pushed, it will be pulled high by the 10K ohm resistor. When the button is pressed, the input will be pulled to ground, and so when the program reads input 3, it will read either a 1 or a 0 depending on if the switch is open or closed. If the switch is open, it reads a 1. If the switch is closed, P3 is pulled to ground and it reads a 0. So in this program on the right here, we have the output 14 statement, which says pin 14 is going to be an output, and we're going to connect that just like we did before to an LED. So that we can turn that LED on and off. And we declared pin 3 to be an input. Now we have our do loop, and in our do loop we're using an if-then-else statement. If, and we look at this condition here, if in 3 is equal to 1, then high 14, that would mean to turn on the LED. Else, meaning in 3 is not equal to 1, it must be 0, then we drive a low on pin 14 and turn off the LED. So as this program runs, the LED should be on all the time until you push the button, then the LED should go off. When you release the button, the LED should come back on. So that is our first introductory slide, and just close that. And so we'll be talking more about P-Basic and the things you can do with the basic stamp, and some experiments, and I'll do some things on my Board of Education that you'll be able to see, and move forward from there. So thanks again, and look forward to seeing you in the next lecture. All right, bye.